Let's look at the absolute value parent function, f of x equals the absolute value of x. Now before we look at the graph of this function or identify its attributes, let's review what absolute value is. Absolute value is the distance a number is from 0 on a number line. For example, the absolute value of negative 10 is 10 because negative 10 is 10 units from 0 on a number line. The absolute value of 0 is 0 because 0 is 0 units from 0 on a number line. The absolute value of 2 is 2 because 2 is 2 units from 0 on a number line. As you can see, absolute value yields either a 0 or a positive number. It will never yield a negative number. Okay, so now let's start looking at what the graph of this parent function looks like. And we can do that by creating an xy table like we have here. And we're going to start by finding our y values. So here we have an input of negative 6. The absolute value of negative 6 is 6. The absolute value of negative 4 is 4. The absolute value of negative 2 is 2. The absolute value of 0 is 0. The absolute value of 2 is 2. The absolute value of 4 is 4. The absolute value of 6 is 6. So we are going to take the x, y values here and form ordered pairs. So I have negative 6, 6, negative 4, 4, negative 2, 2, 0, 0, 2, 2, 4, 4, 6, 6. And now we're going to plot those points. So here is negative 6, 6, negative 4, 4, negative 2, 2, 0, 0, 2, 2, 4, 4, 6, 6. And we can draw in with lines because we know it's not just these points. And this graph will go up into the left forever, so we'll put arrows, and up into the right forever, so we'll put an arrow there as well. If we were to describe this graph, some things that might come to mind is that it's a V shape. It looks like the letter V. The vertex is at the origin, and this graph opens up. There may be some other things that come to mind, and we'll see some more as we identify attributes. So for example, let's look at the x-intercepts. That's where the graph crosses or touches the x-axis. And in this case, there's just one point. So our x-intercept is 0, 0, the origin. The y-intercepts are where the graph crosses or touches the y-axis, and in this case, it is also the origin. So 0, 0 is also the y-intercept. Let's identify the domain. So we could say that x can be any real number. We could use the real number symbol because as we look across our graph and I look at the x-axis, there's no x value that's excluded from my graph. So I could write the real number symbol, or I could say x can be any real number. There are a couple other different formats that I could write our domain in. I could write this in interval notation. That would look like this. So I have curved parentheses, negative infinity, comma, positive infinity. And I could write this in set notation. That would look like this. The set of all x's such that x is an element of the real numbers. Let's look at the range, or the outputs, or the y values. So here, our lowest y value is here at the origin, and our y value there is 0. And it goes up forever until infinity. So I could write my range as y is greater than or equal to 0. In interval notation, this would look like this. I have a squared off bracket, then 0, comma, infinity with a curved parenthesis. I could also write this in set notation. The set of all y's such that y is greater than or equal to 0. So those are my domain and range representations. Then, does this parent function have a max or a min? Well, the parent function has a minimum point, and that minimum is at the origin, 0, 0. If I were asking what the minimum value was, that would be the y value there, which would be 0. I'm going to add another attribute. I'm going to add symmetry. And we could imagine folding this graph over the y-axis here, and this graph would fold onto itself. So we have symmetry over the y-axis, or I could write the equation of the y-axis. I could say symmetry over the line x equals 0.